In the previous video, we had discussed about the two properties of carbon which makes it possible for a separate branch of chemistry to occur, that's organic chemistry, that's catenation and tetravalency. So the shapes of organic compounds is to do with hybridization. So atomic orbitals, when they combine, they lead to the formation of a new set of orbitals called as hybrid orbitals. And these orbitals have an equal energy, and this phenomena of the orbitals forming and getting involved in bonding is called as hybridization. So before we start talking about the hybridization and all of that, let's just recap on the two different types of bonds that are formed. First is a sigma bond. A sigma bond is formed by an end-to-end overlap, or it's also called as a head-on overlap. So you have an end-to-end overlap in case of sigma bonds. Whereas in case of pi bonds, there is a sideways overlap. See, here, this is an end-to-end overlap. This is the sp3 hybridized orbital, and if you notice, it's an end-to-end overlap. Whereas in case of a pi bond, it's a sideways overlap of the half-filled atomic orbitals, and this is called as a lateral overlap. So here you have a lateral overlap taking place, here you have an end-to-end overlap taking place. Now generally sigma bonds are much more stronger than pi bonds because the overlap is to a greater extent. So here there is more overlap of the orbitals compared to the pi bond. So let's start with the organic compounds. Generally we'll be talking about single bonds, double bonds and triple bonds. Alkanes, alkenes and alkynes. In case of alkanes, you will have a single bond between the carbon atom, or the carbon atoms will only have single bonds. In case of alkenes, there will be a double bond involved. In alkynes, there will be a triple bond. So in alkanes, first of all, in the ground state, carbon has 2 electrons in the s orbital and 2 electrons in the p orbital. In the excited state, this electron gets excited and occupies this p orbital, and this leads to the formation of the sp3 hybridized orbitals. So there are 4 sp3 hybridized orbitals over here, and each of these will undergo bonding. All of these will form sigma bonds only. They will not form pi bonds. Pi bonds will require an unhybridized p orbital, which we will see in case of alkenes and alkynes. So here we have methane. Methane's molecular formula CH4. So here this carbon atom is bound to 4 different hydrogen atoms, and the sp3 hybridized orbital is bound to the 1s hydrogen orbital, and this leads to the formation of a sigma bond. This is a tetrahedral shape and its bond angle is 109.5 degrees. Similarly, in this case also you have the formation of sigma bonds only, because this is ethane. Okay, we'll be discussing about the nomenclature at a later point in this chapter. But in ethane, here you have 2 different kinds of combinations happening. First, you have the carbon hydrogen bond. Here again sp3 hybridized carbon bonding to 1s orbital to give rise to a sigma bond. There is also a bond between the 2 carbon atoms, and here the sp3 hybridized orbital of this carbon will bind to the sp3 of the other one to give rise to a sigma bond. So each of these are undergoing bonding, and all of these are sigma bonds because we are talking only about single bonds. So these are all sigma bonds. And in case of our alkanes, in ethane, the CC bond length is 154 picometers. I am telling this because when we compare the bond length of alkanes, alkenes and alkynes, alkanes will have a longer one compared to alkenes and alkynes. This is because the single bond is supposed to be longer than the double, which is again longer than the triple bond. The CH bond length is 109 picometers and the bond angle is 109.5 degrees. So they will arrange themselves in such a way that they will the repulsions between the hydrogen atoms will be less. We'll be learning again, I think you'll be learning about this in the next chapter. So in case of alkenes, they have a carbon-carbon double bond in them. So here in the excited state of the carbon atom, the two orbitals of p as well as one orbital s, all these three will combine to give us an sp2 hybridized orbitals. So they will give us 3 sp2 hybridized orbitals and one of the p orbitals will remain unhybridized. And what happens is here between the carbon, okay, so let's start. Here you have 2 hydrogens and 1 carbon. Each carbon is bound to 2 hydrogens and 1 carbon. So these 2 hydrogens will undergo a sigma overlap with the carbon atom, and this involves the sp2 hybridized orbitals. So sp2 and sp2, and along with that 1s of the hydrogen. So here first you have carbon and a hydrogen 1. Here you have an sp2 hybridized orbital overlapping with an 1s orbital of the hydrogen, and this leads to the formation of a sigma bond. Next are carbon and carbon atom. So first these two will overlap with the sp2 orbitals. Here you have two hydrogens, right? So 2 of them will get used up for binding with the hydrogen. That leaves us with one of the sp2 orbitals, and that is used up for the carbon-carbon sigma bond. Now the unhybridized orbital is still remaining. So what happens is they will undergo something called a pi overlap. So here they are undergoing a pi overlap of the orbitals, and so here you have carbon-carbon bond, okay, and this is between the 2p unhybridized orbitals, and this leads to the formation of a pi bond. Okay, so in case of our carbon and hydrogen, you have a bond between the sp2 and the 1s of hydrogen, sp2 of the carbon obviously, and this leads to formation of a sigma bond. Now the remaining one sp2 orbital is left, and that is getting used up for the formation of a sigma bond with the other carbon atom. Now the unhybridized orbital is used up for pi bonding, and see, so that leads to the, here you have 1, 2, 3 and 4 bonds are formed over here. And this leads to the planar structure. Also one more thing, in case of the bond length of the single bond between the 2 carbons, it was 154 picometers, but in case of this it's a double bond, and that is about 134 picometers. It's much shorter. One more thing, here the bond over here, this is a double bond and it cannot be rotated. If you remember, when we drew a single bond, we'd drawn hydrogens in a way where the repulsions between the hydrogen was considered minimum. So what happens is, if these atoms are closer together, that will lead to the repulsions between the electron clouds of the respective atoms, and that in turn will lead to the instability. Basically it'll make the molecule a little unstable. So about this in detail you'll be, I believe, learning in the next chapter. But notice that the bond length between the double bond is lesser compared to the single bond. In case of alkynes, you have again ground state, you have 2 electrons in the p and 2 electrons in the s. The excited state, you will have this configuration. So what happens is these 2 orbitals will combine to give us the sp hybridized orbitals, whereas the remaining 2 orbitals remain unhybridized, which means these 2 orbitals are responsible for the pi bonding. So here in case of ethine, your CH and CH, we know that the CH is formed by the sp. Okay, wait, let me just sp and sp of the carbon atom with the 1s of the hydrogen, and this leads to the formation of a sigma bond. Okay, and in case of the carbon-carbon, you have triple bond. Okay, which means first of all we know that the one of them would be sp overlap, and this leads to the formation of a sigma bond. The remaining 2 pi bonds are formed by the overlap of the unhybridized orbitals. So here the second and the third will be the unhybridized 2p orbitals, and this leads to the formation of a pi bond. And here, since you have 2, you will have the second one also happening the same way. And that's why you have 2 pi bonds and 1 sigma bond. And this leads to the formation of a triple bond. And here the bond, the angle is 180 degrees, which means it's basically flat, and the bond length is 120 picometers. If you remember, we discussed that in case of the double bond, the bond length was 134 picometers, whereas in case of the single bond, it was 154 picometers. So in case of a triple bond, it's much shorter, and the bond length between carbon and a hydrogen is 106 picometers. With that, we finish the shape of organic molecules. In the next video, we will be discussing the in-text questions related to this, so do check it out.